ladies and gentlemen, and welcome to Mr. Saucedo's YouTube videos. Today we're going to be going over Chapter 7 in Zumdahl, the 7th edition, which is all about atomic structure and periodicity. So to start with, let's talk about Section 7.1, so electromagnetic radiation. So one of the ways we introduce this unit is by talking about fireworks. So if you've ever been to a fireworks show before, you probably noticed that you have multiple different colors of fireworks that can appear in the sky. And so depending on what the chemical makeup is of the color-producing compound in the firework, you can make different colors. So strontium, for example, makes red, or calcium makes orange, or sodium makes yellow, barium green, copper blue, and then purple contains normally copper and strontium, but there are plenty of other ways you can use potassium or something in order to make kind of a purpley color. So the question becomes, and the driving kind of question that I like to frame this unit in, is where exactly do these colors come from? So when we burn strontium, we get this red light. Where exactly is that red light coming from? And why do certain chemicals that we burn give off different colors than other chemicals do? Some chemicals maybe don't even give off any color, or at least no color that we can see. So the questions that I like to consider when going through this unit to kind of frame us are these two questions. So let's explore a little bit about electromagnetic radiation. So electromagnetic radiation, and I'm going to abbreviate that as EMR, is just one of the ways that energy travels through space. So we haven't really discussed energy very much yet, but energy has multiple forms and can be stored in many ways. You know, we have kinetic energy and potential energy, right? Well, electromagnetic radiation is just one of the ways that energy can travel through space. And it's the one that is kind of the important part, let's say, of the unit that we're going to be talking about. So what characteristics do or does electromagnetic radiation possess? So there are a lot of characteristics, and so these are the three important ones, but we're going to also say that there are more than just that. So, you know, we have wavelength here, frequency, let's say, you know, speed isn't even really on here because you need to know wavelength and frequency to find it normally. And then we have amplitude, crest, trough. So there are a lot of different parts to a wave. And the ones that aren't listed here, they're going to be, they're not really that important, but I'm going to kind of just tell you about them before we move on to the next slide where these are defined. Okay, so one of which is the word crest. So a crest is the top part of a wave. It is the highest point, let's say, that a wave can reach. So this would be a crest and this would be a crest. A trough is the lowest part of a wave. And so this would be a trough, and again, this would be a trough because this wave is completely symmetrical. Amplitude is the distance from the origin, which is like the center of the wave, all the way to the crest. Or incidentally, if it's a symmetrical wave, right, the origin, meaning the center of your wave, all the way to the trough. So amplitude would be equal in both of these cases. Okay, so let's actually discuss the wavelength, frequency, and speed, since these are the big important ones. So what sort of characteristics do we see? So wavelength is abbreviated as this Greek symbol called lambda, and it's the distance between two consecutive peaks or troughs. So just the distance, and you can measure that using whatever measuring tool you'd like. In fact, I'm going to show you a little simulation in a second that uses a ruler. Frequency. All right, so frequency is abbreviated as, it looks like the letter V, but it's actually the Greek letter nu, and it's the number of waves per second that pass a given point in space. So most frequently, no pun intended, the way that we see frequency as a unit is in hertz. So wavelength, we normally think of that in nanometers, especially when we're talking about, you know, visible light. But generally, you know, wavelength, we're going with SI units of measurement, it would be meters. So you would measure wavelength in meters. Frequency, on the other hand, really isn't unitless. Okay, that's not the way to think about it, because look at it. It's the number of waves per second. So it really is just inverse seconds as a unit. So you can picture, you know, s to the -1. That would really be what frequency's unit is. And so because s to the -1, like inverse seconds, sounds and looks weird, the unit is just hertz. they're equivalent to each other, okay? And so frequency is literally how frequently, how many waves are passing a point in a given second. What about speed? So speed is abbreviated as the letter C. And when we say speed of electromagnetic radiation, we're actually talking about the speed of light. And so that is a constant in a vacuum at 2.9979 times 10 to the 8th meters per second. So notice that in order to get speed here, wavelength would need to be in meters, and frequency, inverse seconds, would need to be in, you guessed it, inverse seconds, or hertz, okay? So now let's take a look at some examples here of waves. So here is a good simulation. It's a PhET simulation, wave on a string. Okay, that's actually the title of it, right? So you can see the properties that this wave possesses, and in fact, we can even do it in slow motion. So you can see that we have peaks at the high point here, right? We have troughs. You have the origin, which is like the middle or center point of this wave. And then if we wanted to measure the wavelength, what we would do is we would just take our ruler and we would drag it. And then we would, estimate, in this case, it's in centimeters, but here, let's say, that's 0, that's 4, let's say that would be 0.2, so about 4.2 centimeters or so, or 4.20 centimeters. That would be my wavelength in that situation. And so again, it literally is just the length from one peak to the next peak, or from one trough to the next trough. And so since this is a symmetrical wave, which, electromagnetic radiation is, we could also do the same thing here. And you'll notice that from this point to this point, it's still about 4.20 centimeters. Okay, so that's how you would get your wavelength. Now notice what happens if I change the frequency. So I'm going to move this back to normal. Now let's make this more frequent. Notice that more waves are passing a point in a second. Let's make it less frequent. Now there are less waves passing a point in a given second. And so again, frequency is really just a way of looking at how many waves are passing a point in a second. If something is frequent, there are a lot of waves passing it in a second. On the other hand, if it is not as frequent, then there are fewer waves passing it in a second. All right, so let's actually, now that we've defined wavelength and frequency and speed, what is our formula then? Our formula is the speed of light is equal to the wavelength of light times the frequency. If I multiply these together, I would get the speed of light. And if you get more than that, it's impossible. So the speed of light is literally a barrier. It is a constant. So you can't go, no electromagnetic radiation go faster than this. This is considered, again, impossible. So the nature of waves. So again, here's just some pictures. We're used to seeing like ocean waves like this, and light waves are a little bit different than ocean waves, but you can get the idea here that this is less frequent. So again, 4 hertz, 4 cycles per second. Here we have something that's more frequent. We have 8 hertz per second. And then here we have, again, something that is moving way more frequently. And so again, if the distance from here to here is a second, then you can basically count how many waves you have. Like you can count the peaks, and that would tell you approximately how many waves you get per second. So how do we classify electromagnetic radiation? Well, there are many different types of electromagnetic radiation. Okay, that's the first thing. And the part that you can see is just this tiny, tiny, tiny little sliver that we call visible light. And so yes, visible light is extremely important. And since we're talking about, fireworks and colors that we can see, obviously the visible spectrum is going to be the one that we're going to spend the most time on. But also, we have infrared, microwaves, radio waves, ultraviolet, X-rays, and gamma rays, all of which are things you cannot see, but are still everywhere. For example, right here, we have radio waves, and notice that this scale is wavelength in meters. So radio waves are gigantic. Okay, they are huge. They are like, these gigantic, really large crests that are, that are measured sometimes in, kilometers. They're gigantic. And so those are the weakest form of radiation. And then as we get, smaller wavelengths, things get a little bit more powerful, let's say. And so we have microwaves, which have more energy than that and can cause molecules to rotate around. We have infrared, okay, which is normally what we consider heat or thermal vision. If you ever look at kind of like Call of Duty style stuff where you can see in night vision goggles, that's all seeing infrared. Okay, then we've got visible light, which of course we know, red being the weakest of the colors, and then violet being the strongest of the colors, the one that has the shorter wavelength in this case. Ultraviolet is way more powerful than visible light. It can cause sunburns. We have X-rays. Everybody's familiar because you've all gotten X-rays before. And then gamma rays are released by exploding stars and nuclear explosions and stuff like that. So electromagnetic radiation can be classified into any one of these, but visible light is the one that we're going to spend the most time in, and a little bit in the ultraviolet, and a little bit in the infrared. Right, so the nature of matter, 7.2. Energy can be gained or lost only in whole number multiples. So we're going to talk about what this means, but HV, multiples of HV are really what we're talking about here. Okay, so H is a constant. It's called Planck's constant. And then this little V is, again, not really a V. It's the Roman letter nu, and that's frequency. So if you multiply Planck's constant by the frequency, energy can only be lost in whole number multiples of Planck's constant. Okay, and so what that means for us is that energy can only be transferred in whole quanta. So if you've ever wondered what quantum mechanics is, or what the word quantum means in quantum mechanics, it comes from this idea that only whole number multiples of this can be transferred energy-wise between atoms and from atoms. And so we call that little packet of energy a quanta, is what that's technically called. So keep in mind, though, that even though we're looking at it like it's a whole little piece, light seems to have not just properties like particles, like you can think of this as being like a particle thing, but it also has wave-like properties like we just talked about, that wave demonstration. So again, tons of weird stuff happens when we talk about the nature of matter and the nature of light. So the important thing to get out of what I just said is that energy is quantized, meaning that, again, it can only exist within multiples of Planck's constant times frequency. And so electromagnetic radiation, okay, again, can be thought of as a stream of particles. So like I just said on the last slide, even though it has wave-like properties, like with frequency and wavelength and all those kinds of things, it also has, particulate properties where it seems to act sometimes like they're physical particles, not really waves. So we call these particles photons, the word photo meaning light, and then on kind of like, proton, neutron, electron, they're trying to make them all kind of end the same way. So particles of light are called photons. And so, interestingly enough, the energy of a photon is equal to Planck's constant times the frequency. And another way of writing that would be Planck's constant times the speed of light divided by the wavelength. So these are both equivalent to one another and can be used to solve problems. So if I ask you, what's the energy of this wavelength of light, you could very simply find, the wavelength and enter that as your, little bottom part of your fraction, multiply Planck's constant by the speed of light, and then just divide by that number, and that will tell you how much energy that light has. And so what is Planck's constant? We've been dancing around it, but Planck's constant is equal to 6.626 times 10 to the negative 34 joules seconds. So this is joules, that's a unit of energy, times seconds, and so it's pronounced joule seconds, okay? But that's Planck's constant. And so let's talk a little bit about how this can be utilized in a little Nobel Prize winning effect that was discovered by Albert Einstein called the photoelectric effect. So here's a picture of the photoelectric effect. And I decided instead just to show you a little simulation of it because I thought it'd be easier to understand. So here's kind of what the photoelectric effect is all about. So let's say that I have sodium metal. Okay, and so I have this little thing hooked up to a battery. There's no current flowing through the battery currently. And I'm going to shine light on this sodium metal plate. Okay, right now the light that I'm shining has a wavelength of 673 nanometers. There's no current flowing through it. So traditional physics before Albert Einstein came around would say, or should say, that if we just leave this light shining on here, eventually it would build up enough energy to send some electrons over and build up a current. But we know that doesn't happen. So what Einstein discovered was that it takes a certain amount of energy in order for this process to occur. So let's move the slider. So remember, red is the weakest, so let's do orange, nothing. Okay, let's do yellow, nothing. Let's do green. Let's slowly go towards blue, and now notice, okay, we're starting to get electrons moving. Traditional physics or classical physics up to that point could not explain this process at all. Like there was no way of explaining this. And so notice that when when this process occurs, now we have electrons that are moving over. And so as we get and move up to stronger and stronger wavelengths here of light, we're getting more and more current being generated. And so this is what the photoelectric effect is. And so notice that now we're getting into purple, and we can even go to UV if we want to. We can get like super energetic stuff that we can't even see. And so again, the idea being that there seems to be a magic point at which all of a sudden, okay, current will start to flow and electrons will start to move. And so this could not be explained using classical physics, but it could be explained using, let's say, a modern idea of quanta and photons. And so that's what the photoelectric effect is really all about. It's about a shift from classical physics to modern physics. And so something that's a little interesting is that, yes, energy has mass. Something else that, Einstein discovered, E equals mc squared. So energy has mass. And so that means that light really has a dual nature to it. It exhibits electromagnetic radiation like wave properties, right? So electromagnetic radiation, and in fact, you yourself, being made up of matter, we exhibit wave-like properties, which is super, super weird because, again, does it look like we exhibit wave properties? No. Would we be able to measure our wave properties? It'd be really, really difficult to do that because, again, radio waves go on for kilometers. Our waves that we generate would go on for probably longer than that. And again, particulate properties, like clearly we're made up of particles, but light also sometimes acts like it's made up of particles, sometimes acts like it's made up of waves. And so now let's talk a little bit about the atomic spectrum of hydrogen. So first of all, let's explain a couple of things before we talk about, the simplest of the elements, hydrogen. What is a continuous spectrum? So a continuous spectrum is the result of when white light is passed through a prism. White light contains all of the visible wavelengths of light that we can see, okay? A line spectrum, instead, is showing just discrete wavelengths, okay, of light. So for example, if instead of passing white light through a prism, if we were to heat up hydrogen, turn it into a plasma, and then put that light through a prism, this is what we would see instead, which is super weird. You would only see these four lines. So the question becomes, why do these lines appear for hydrogen? And why is everything else not there? only these four lines appear when you pass hydrogen light through a prism, whereas usually what we would get is something like this. This is white light traveling through a prism, and so you get red at the top, and then, which has the longest wavelength, and then it goes all the way to the shorter wavelengths until you get to purple at the bottom. And so white light does that. All right, so let's talk about the line spectrum for hydrogen. So you saw those four lines, and it's, again, really easy. And so in case you don't know what I'm talking about right here. You see these. It's really easy to kind of say, okay, great, this is what the emission spectrum of hydrogen looks like, but it's clearly a picture, right? So what I wanted to do was to show you it in motion. And so the easiest way to do that is to actually use what we call an emission tube. So that emission tube has hydrogen that's heated up by electricity. And so what you do is you use this special little filter. And so as the light travels, it's getting filtered, and you can see those lines actually in reality. One of them is almost impossible to see via this little demo, but this actually is filtering out those lines. So you can't really see the blue one, but you get the idea. This is what the line spectrum of hydrogen looks like. And so the question is, why exactly does this occur, right? Like, why do we have these little lines? So the significance is this. So let's pretend that I have a hydrogen atom right here. Okay, actually, this isn't a hydrogen atom necessarily, but let's say it's any atom. Okay, and I am shooting it with a bunch of energy. And so when I shoot the energy at it, what's actually happening? Most of the energy is going to pass straight through the atom without it actually interacting with the atom at all. But there is going to be a frequency. In fact, there are going to be many frequencies that are going to be of the correct energy that the electron or electrons in the atom are actually going to absorb that particular wavelength of light. And when it does that, it will become excited. And so when that electron becomes excited, it will absorb that energy, and then eventually it will give off that energy. And so what you'll get is a blip, a little line in your spectrum. So notice right here we go, we have these 5 colors going in. And so from the point of view of the observer, if we were just, on the opposite side here, this is what we would see. We'd see all the colors of the rainbow except for that particular shade of orange. But if we were looking at it through that little prism from the perspective of the hydrogen here, what we would see is just the orange. That's all we would see. And so that's the significance of the atomic spectrum of hydrogen. Now notice orange is not even a part of the spectrum of hydrogen at all, but only certain energies are allowed for the electron in a hydrogen atom, which sounds an awful lot like quanta, right? HV, that whole thing, energy equals H times V. And so energy for electrons in a hydrogen atom is quantized, meaning, again, only particular frequencies are allowed to be absorbed. So why is it significant that the color emitted from the hydrogen emission spectrum is not just white light? So again, classical physics would say that it should be white light, that, hydrogen should, or all elements should just, kind of emit all of the colors of the rainbow, and we would see that as white. Now, how does the emission spectrum itself support the idea of quantized energy levels? Well, again, only particular colors are showing up, which means that if you know the energy that, we are getting from this, we should be able to calculate all of this out. Okay, we should be able to use the frequency to calculate the energy that that photon has and be able to figure some stuff out about it. So this takes us to the last section we're going to cover today, which is section 7.4, the Bohr model. So electrons in a hydrogen atom, according to Bohr, okay, this is the Bohr model, move around the nucleus, and only certain circular orbits are allowed. So Bohr's model actually gave hydrogen atoms energy levels. And so the energy levels were consistent with the hydrogen emission spectrum. So again, using the calculations, so using E equals H times V, he was able to figure out, okay, what are the energy levels that hydrogen atoms should possess? And so what he did was he marked them as these numbers. N equals 1 being the first ring, N equals 2 being the second, 3, 4, 5, 6, 7, etc. And the idea was that you just have one electron that's orbiting like, a planet around the sun. I almost said the star, the sun. And so when you are giving that electron energy, what happens is it moves from one energy level to another energy level. If you give it enough energy, it can go, all the way to 7. But generally speaking, you only give it enough to go up 1 or 2 energy levels, and then it has more energy, and then eventually it will shoot off a photon of light and drop back to its original energy level. And so that's Bohr's model of the hydrogen atom, and it perfectly explained the hydrogen emission spectrum. You could actually use these energy levels and calculate and find, okay, you would get a red wavelength of light around what that little spectrum showed. You would get, a green wavelength of light around what that spectrum showed. And so what we call the ground state is the lowest possible energy state. And so for hydrogen, go figure, it's N equals 1. It's, just right here at the bottom level, okay? So here is a visual representation for the electronic transitions in Bohr's model of the hydrogen atom. So you can see that to get from energy level 1 to energy level 2 is quite a jump. To get from 2 to 3 isn't as much. To get from 3 to 4 isn't as much. To get from 4 to 5 isn't as much. But what we get when we jump, so let's say you are a little electron and you're zipping around and you get enough energy to jump all the way from here all the way up to 3, and then you get enough energy, and let's say, sorry, not enough energy, then you lose that energy and you drop down to 2, what you'll get is a red wavelength of light. Let's say instead, you're right here and you go all the way up to 4, and then you drop down to 2. Well, then you get a green wavelength of light. And then let's say, you jump up from here, again, the ground state, all the way up to 5, and you drop down to 2, you get a blue wavelength of light. And so that's what we call the energy level diagram for the electronic transitions. It's just a visual representation where the distance from here to here is increased energy. How much energy would it take to do this? And then the distance, the number 1, 2, 3, 4, 5 indicates how far away from the nucleus the electron now is in that hydrogen atom. All right, and so now the last one is a different view of the Bohr model for the hydrogen atom. And so this is called the orbit transition diagram. And so instead of just looking at lines up and down, now we're looking at, here's the nucleus, and then here is, the N1 energy level. And again, you can picture a hydrogen atom just kind of moving around. A hydrogen atom, an electron, just kind of moving around it. And then this would be energy level 2, 3, 4, etc., going all the way up. So you can picture this as being the nucleus. This is N1, this is N2, etc., going up. And so again, the transitions that we see here are equivalent to these different lines, okay? And so I wanted to show you a little simulation of the Bohr model of the atom, just so you can get an idea of what we're talking about. All right, so here's our simulation. So we've got our hydrogen atom, we've got a proton here, we've got our electron, which is at what? N1, 2, 3, is already at N4, but that's because this was going on for a while. But anyway, you get the idea. So we have our electron, we've got our proton. Each one of these rings represents N1, N2, N3, N4, N5, all the way up to N6. So we've got 6 energy levels going all the way up. And then this is our spectrometer. So that spectrometer thing is where we saw those little colored lines. So what we're going to do is we're going to basically, for all intents and purposes, spray the screen with energy like this, okay? And so every time you see a little blip here, this would be a color of light that would be being released by this electron as it moves further and further down. So notice that the electron's doing its thing, and every now and then it gets hit by something that has enough energy in order for it to jump up an energy level or 2. And so what we're going to do is we're going to make this go super, super, super fast. And so you can see, oh wow, and it's going really fast now. But we've got, some of the stuff we can't see. Some of these energy level transitions are in the UV. Some of them are in the IR. We can't even see those. But we can definitely see the cyan one. We can see the red one. And so eventually, as we let this run for an infinite amount of time, eventually what we would see are all of those little visible lines showing up that we saw in our original picture. And so see, like right now we got like the little kind of purpley looking one. So all we're really missing, yeah, there we go, perfect. Now we've got technically all of the ones that we can see. We've got the little cyan one. We've got this blue one, which is really, really difficult to see. I guess it's more of an indigo, purple, and then red. And then look at all of the UV and all of the IR. So this is infrared. We can't see these, but the hydrogen atom is actually giving off, when it does some of these transitions, infrared light. And then here it's giving off ultraviolet light. Again, stuff we technically can't see visibly, but we can still see these 4 lines, okay? And so that's the idea behind Bohr's atom and Bohr's model of the atom. Now, important to our situation, let's say here, is that for a single electron to transition from one energy level to another, that can be calculated. And the way that it works is by this. So this is the change in energy. It's equal to negative 2.178 times 10 to the negative 18 joules times 1 over n squared, being, again, the final transition, minus 1 over n squared, meaning where did you start? The initial transition. That's what n is going to be. And remember that on Bohr's model of the atom that we just saw, that only had 6 levels that were possible. On the first one, there were 7. So we're really limited in these numbers. So there are not an infinite number of transitions that you can have. There's a limited number of transitions you can have, which again explains why we only see 4 visible lines on hydrogen's emission spectrum. All of the rest are in infrared or they're in the ultraviolet. So they're more energetic or less energetic. And like it says again, that's the change in energy. N final integer here, final distance from the nucleus, that's again an integer between 1 and 7, and then initial, same thing. And we can calculate and find out, okay, we can actually get these colors that we were just talking about by doing this type of calculation, okay? Now, the interesting part is that this model perfectly fits the hydrogen atom. And again, it perfectly fits the idea that energy levels are quantized, meaning that only certain energies are allowed and required, and Bohr's model perfectly fits this. So as the electron becomes more tightly bound, its energy becomes more negative, related to the 0 energy reference state. As the electron is brought closer to the nucleus, energy is released from the system. This just explains, again, moving from an excited state to a ground state. So Bohr's model is, as we would expect, a perfect representation of the hydrogen atom. Now, why don't we use Bohr's model? Right? Why don't we just use Bohr's model? It doesn't work for any other element, which is kind of sad, but it only works for hydrogen. That's the only model that perfectly can be modeled is hydrogen. Otherwise, Bohr's model falls apart and doesn't work any longer. And the reason why is electrons do not move around the nucleus in circular orbits like Bohr originally envisioned. Okay, so that little like circular motion, that's not what electrons do at all. And so even though Bohr's idea is, pretty cool and perfectly explains hydrogen, it doesn't work for helium. And all helium has is 1 extra electron, right? That's all it is. It's just an extra electron. You'd think it would be super easy to take Bohr's model and apply it to helium. And he tried desperately and it didn't work. Okay, so that's where we're going to stop for the day. Come back again later on for our second part of chapter 7 in Zumdahl, the 7th edition. Thank you for watching. Please make sure that you like and subscribe. And if you have any questions, let me know in the comments.